So our first question asks us to draw the Bode plot for the following transfer function: s plus 10 over s times s squared plus 3s plus 50. We start this problem by first rewriting this transfer function in proper format. This means factoring out the constant term in each of the polynomials in our transfer function. So we factor out the 10 from the numerator and the 50 from the denominator. This is done in order to allow us to separate our transfer function into distinct parts. We have a constant gain term, a zero term, at 10, a pole at the origin, and finally a complex conjugate set of poles originating from the last second order term. For Bode, we can draw the individual Bode plot of each part and then combine them together to get the final Bode plot of the entire transfer function. As a reminder, when g of s equals a constant gain term, the magnitude plot contributes a constant value equal to 20 log of the constant gain term k. The phase plot contributes 0 degrees if k is greater than or equal to 0. If k is less than 0, then the phase plot contributes negative 180 degrees. When g of s equals a single zero term, the magnitude plot returns a constant value of 20 log of the value of z, and then increases in the slope of contribution by 20 decibels per decade when it achieves a frequency value of z. This is for the situation when z is greater than 0 and less than 1. If z is greater than or equal to 1, then the magnitude plot contributes 0 decibels until it achieves a frequency value of z, at which point it begins to contribute an additional 20 decibels per decade. The phase plot contributes 0 degrees until it reaches a frequency value of z over 10, or 1 decade before z. It then increases to a slope of 45 degrees per decade and stabilizes to a final value of 90 degrees when it reaches a frequency value of 10z, or exactly 1 decade after z. When g of s equals a single pole term, the magnitude plot returns a constant value of negative 20 log of the value of p, and then decreases the slope of contribution by 20 decibels per decade when it achieves a frequency value of p. This is for the situation when p is greater than 0 and less than 1. If p is greater than or equal to 1, then the magnitude plot contributes 0 decibels until it achieves a frequency value of p, at which point it begins to contribute an additional minus 20 decibels per decade. The phase plot contributes 0 degrees until it reaches a frequency value of p over 10, or 1 decade before p. It then decreases to a slope of minus 45 degrees per decade and stabilizes to a final value of minus 90 degrees when it reaches a frequency value of 10p, or exactly 1 decade after p. Finally, when g of s equals a complex conjugate pole term, the magnitude plot contributes 0 decibels and begins to rise slowly. It then reaches a peak of minus 20 log of 2 times zeta times the square root of 1 minus zeta squared. This peak is achieved at a frequency of omega n, which is dependent on the specific form of g of s. After reaching this peak, the plot decreases to a slope of minus 40 decibels per decade indefinitely. The phase plot contributes 0 degrees until it reaches a frequency value of omega n over 10 to the power of zeta. It then decreases to a value of minus 90 degrees at a frequency of omega n. It then decreases even further to a value of minus 180 degrees at a frequency of omega n times 10 to the power of zeta. The phase plot then stabilizes to a value of minus 180 degrees. So now, after that quick reminder, we can begin applying these rules to our own transfer function. So we can draw the Bode diagram of each individual part. The static gain term of 1 over 5 returns a magnitude of 20 log k, or negative 13.97. Since k is larger than 0, the phase plot returns a value of 0 degrees. Since our 0 value is 10, which is larger than 1, our magnitude plot returns a value of 0 until it reaches a frequency value of 10, at which point it achieves a slope of 20 decibels per decade indefinitely. As an example, at a frequency of 100, it will have a value of 20. The phase plot begins at 0 degrees. It increases its slope to 45 degrees per decade at a value of z over 10, or 1. The slope then stabilizes after 2 decades, and the value remains constant at 90 degrees. Since our pole is at the origin, it always has a slope of minus 20 decibels per decade. However, we know its relative position on the plot because a pole at the origin will always intersect the horizontal axis at a value of 10 to the power of 0, which is effectively just 1. As for the phase plot, since the pole is at the origin, it always contributes minus 90 degrees regardless of frequency. Now finally, for the complex conjugate pole term, we know the general form. However, we need to obtain the values of omega n and zeta. Comparing our term to the general complex pole term, we see that omega n squared is equal to 50, meaning omega n is approximately equal to 7. Once again, through comparison, we see that 2 times zeta times omega n is equal to 3. Since we know that our omega n is equal to square root of 50, we get that zeta is equal to 0.21. This tells us that our magnitude plot peaks at a frequency of 7, and the peak value obtained is approximately 7.9. For this same term, the phase plot starts at 0, decreasing slope at a frequency value of 4.36, achieving minus 90 degrees at a frequency of 7, which is omega n, and finally stabilizing at a value of minus 180 degrees at a frequency of 11.5. Having drawn the Bode diagrams of all the individual parts, we can now combine these plots to draw the overall Bode diagram of our transfer function. We simply overlap all 4 plots and then obtain the sum of the plots at each frequency value to obtain the final plot. Our final plot begins with a slope of minus 20 degrees per decade due to the single pole term at the origin, until it reaches a frequency of 10 to the 1. The Bode diagram peaks at a frequency of 7 due to the complex pole term. And finally, the plot eventually decreases to a net slope of minus 40 decibels per decade. Similarly, we overlay the phase plots and sum the total values to obtain the final plot. Our final phase plot starts at minus 90 degrees due to the pole at the origin. It achieves a peak at 4.36 and a trough at 11.5 due to the complex pole term. Finally, it stabilizes to a value of minus 180 degrees. And there you have it. That is our final Bode diagram.